Okay, so we are going to talk about digital signatures. So I'm going to talk about digital signature algorithm or digital signature standard, which is actually no longer preferred. So I have to give it as an example to see what people used in the past. But generally, I prefer algorithms that work on elliptic curves. So elliptic curve digital signature algorithm should be your choice. And Bitcoin also does that. Okay, it doesn't use this one. But in order to understand the elliptic curve digital signature algorithm, it is nice to understand the main digital signature algorithm. So a digital signature is a number dependent on some secret known only to the signer's private key in this sense, and additionally on the contents of the message being signed. Due to the sizes of the signatures, hash of the message is signed instead of the message itself. So think about it in this way. So you are going to build a driver, for instance, NVIDIA's CUDA drivers. They might be more than 1 GB. Signing that driver will give you a signature that will be larger than 1 GB. Instead, you hash it like using SHA-256. So the result is 256, but then you sign it, so your signature will be small. Signatures must be verifiable. If a dispute arises as to whether an entity signed a document, an unbiased third party should be able to resolve the matter equitably without requiring access to the signer's private key. This is how we can actually use Bitcoin or similar cryptocurrencies, because when you make a transaction, nobody can claim that it is wrong, or if you create a fake signature, everybody can understand it without asking for the private key. Disputes may arise when a signer tries to repudiate a signature it did create. So you send a transaction in Bitcoin and claim that it wasn't you. But people will check the signature and they will say that no, this signature belongs to you. Or when a forger makes a fraudulent claim, again, everybody can use the public key to verify if it is valid or not. So digital signature schemes can be used to provide the following basic cryptographic services: data integrity, the assurance that the data has not been altered by unauthorized or unknown means; data origin authentication, the assurance that the source of the data is as claimed; non-repudiation, the assurance that an entity cannot deny previous actions or commitments. An important thing, there's a huge misconception. Since a digital signature algorithm is similar to an encryption algorithm, people refer to it as an encryption, but a digital signature algorithm is not an encryption algorithm because it doesn't provide confidentiality. When you sign something, you also give them the message that this is the thing I signed. So there's no secrecy involved. There's no confidentiality involved. So this is not an encryption. We call that in an encryption. We have the plain text, we convert it into ciphertext, and only the person we want to communicate can decrypt it and obtain the plain text. This is also important because when you ask ChatGPT, like artificial intelligence systems, and you ask if Bitcoin has encryption involved, and they say that yes, everything is encrypted in Bitcoin. And with confidence, AI says that every transaction is encrypted and then written onto the blockchain. But actually, there are no encryption algorithms involved in Bitcoin or Ethereum or similar cryptocurrencies. Okay. Digital signature algorithms or hashing algorithms are not encryption algorithms. Digital signature schemes are commonly used as primitives in cryptographic protocols that provide other services, including entity authentication. There are many standards like this. Authenticated key transport. There are many, again, old and revised standards like this. And they're also used in authenticated key agreement standards like this. So we use digital signatures a lot in many scenarios, and you can check these standards if you're interested. So let's focus on digital signature algorithm, DSA, or the other name is digital signature standard, DSS. The DSA was proposed in August 1991 by the US National Institute of Standards and Technology. It was specified in a US government Federal Information Processing Standard, FIPS 186, called the Digital Signature Standard. DSA can be viewed as a variant of the algorithmal signature scheme. Its security is based on the interoperability of the discrete logarithm problem in prime order subgroups of ZP star. And when I was teaching last year, I said that the current draft of this FIPS 186.5 was in draft version, and there it said they removed the digital signature algorithm from the new version, and they say that prior versions of the standard specified the DSA. This standard no longer approves DSA for digital signature generation. DSA may be used to verify signatures generated prior to the implementation date of the standard. See FIPS 186-4 for the specifications for DSA. As you can see, United States no longer using this signature algorithm. Instead, they prefer elliptic curve digital signature algorithm, by the way, or similar variants. But again, in order to understand it, it is a nice idea to see how DSA works. Let's focus on parameter generation. First, you choose a good hash function, like SHA-2 and SHA-3. No MD5, no SHA-1, okay? You choose two key lengths, L and N. So in order to have 128-bit security, you can choose these numbers as 3072 and 256 bits, okay? Choose n-bit prime Q. Here, as an example, I said it can be 256 bits. Then choose L-bit prime modulus P such that P minus 1 is a multiple of Q. So P is a lot larger than Q, but Q should divide P minus 1. This is how you choose it. Okay. Choose G. Its multiplicative group order modulo P must be Q. So then parameters P, Q, and G may be shared between different users of the system. So for instance, if you want to communicate with two people, you can generate these parameters for both of them in a different way, but you can choose these parameters only once and use it with everybody else in the system. And this is how Bitcoin or Ethereum works. Of course, they don't use this. They use elliptic curve parameters, but they choose the parameters for once and everybody keeps using it. So this parameter generation can be only done once if you prefer. Next, everybody who is going to use this system has to generate their secret keys and public keys, right? So as the secret key, you randomly choose a secret key X, as in the case of what we did in El-Gamal encryption algorithm. Then you calculate the public key Y equals to G to the X mod P, right? Y is your public key, G is your secret key. Again, if you can solve the skill logarithm problem, you capture the private key. So let's look at signing. Somebody wants to sign a message. This is important. For every message, you have to randomly choose a number K and never use it twice, and this has to be kept secret. If you sign two different messages using the same K, your private key is lost. People did in the past, there was a bug in a wallet software in Bitcoin where they used a Java random number generator, but there was a bug. So it used the same random number twice. So you create an account, for instance, you send a few Bitcoins to your friends. Months later, you send different amount of Bitcoins to somebody else, but that instant, people capture your private key and withdraw all of your money from your wallet. So this is important. Randomly choose K. It has to be secret, and it has to be different for every message you sign. Calculate G to the K mod P mod Q. You calculate R. You calculate S as follows. M is your message that you want to sign. You calculate the hash of it. You add X plus X times R. Recall that X is your secret key. R is from here, okay? And K inverse is the inverse of the random number you chose, okay? So your signature is R and S. Actually, any Bitcoin or Ethereum transaction is just like a signature like this. Again, not DSA directly, but you do these operations not in mod Q, but you do these additions, these multiplications and so on as elliptic curve group operations, okay? But anyway, this is how you sign anything. And now everybody has to verify your message to check if you really signed it. What they do is as follows. Since this is your signature R and S, they calculate S inverse, obtain W. They calculate the hash of your message. Again, message is not secret, so this is why this is not an encryption algorithm. The message is publicly available to everybody. So as the verifier, you calculate the hash of the message, multiply it with W, which is you just calculated here, and obtain U1. Then you calculate U2, which is R times W. Again, R is coming from signature. W is what you calculated here. Now you calculate G to the power U1 times Y to the power U2, modulo P, modulo Q, and end up with V. So if V equals to R, then the signature is valid. So you might think that why this is the case, just, go back to all of these calculations and you will see that here you are actually hiding your private key to this S, and it is removed from there with this basic number theoretical arguments actually. Okay. The security of DSA or DSS relies on two different discrete logarithm problems. One is the discrete logarithm problem in ZP star, because this is the group we are working on, right? This is the field. So there's a number field sieve algorithm. This is a sub-exponential time algorithm. This is why actually the group size has to be large, like 3000 bits. And by sub-exponential, as I mentioned, it is not polynomial, not exponential, but something in the between, like this in the big O notation. It doesn't look nice, but as you can see, it's a little bit better than exponential time algorithm. Second discrete logarithm works to the base G in the subgroup of order Q in ZP star. Given P, Q, G, and Y, find X such that Y is congruent to G to the X mod P. For large P, for example, 3032 bits, the best algorithm known for this problem is Pollar's row method and takes square root of with respect to Q over 2. This is why, actually, I'm forcing you to choose P as 3072 bits if you want 128-bit security, due to this number field sieve algorithm, which is sub-exponential. Also, you choose Q as 256 bits due to the square root coming from the Pollar's row algorithm. Okay, this is the main mathematical reasoning behind all of these choices.